All right, so we're down to, today is the 20th, so we're down to Chapter 10, Untrusted Input. Let's talk about that. I should have it open in one of my windows. Somehow I don't. All right, it'll take me a minute. Well, it won't take me a minute. It'll take me a few seconds to click to the right place. There we go. All right. So we'll talk about input validation, how to perform it, character string vulnerabilities, injection vulnerabilities, and how to mitigate them. So input validation is, of course, the huge issue when you're constantly taking data from an untrusted source, like the user, typically putting things logging in. So input validation is limiting what they put in. Make sure the username only has a reasonable number of characters. If you're taking a number of hours, make sure it has some limits. And so your attack surface is anytime you get data from outside your program from some uncontrolled source, including other modules of code, which is probably the #1 problem in web apps, is you have many different services running, written in different languages, sending signals to each other, and one part of it, one module will send out a signal which is misunderstood by the next module. It's modern web apps are very much like you have a team where one person speaks Japanese and one person speaks English and one person speaks only German, and they're trying to communicate with each other. The misunderstandings between the modules are common. So to determine validity, however, you have to know what valid input values are going to be and disallow all the rest. So, you know, if you're putting some headroom is good, allocate a 4096 byte buffer and limit inputs to 4000 bytes. It's good to leave a little bit of room, because if you get too close to the edge, little things will hurt you. And so here's common, this is the recommended order in which to do validation of input. First, make sure it doesn't exceed a maximum size, because one simple denial of service attack, of course, is to just send like 1,000,000 bytes in to the field that expects a name or a password or a credit card number or something. And obviously you want to reject that right away, because any attempt to process something that huge is either going to make your system crash or at least slow it down, and obviously it's wrong. So first make sure it's not too big, then make sure it's in the right format, and then make sure it's in a reasonable range of values. And you pretty much have to do it in that order, because it has to be in the right format or you can't quantify it. Like if there are letters in a numerical field, then you can't really compare it to a maximum value. All right, so that's the thing. All right, so another thing that's useful is to realize that your non-programmers should be able to understand the limit, a normal human, for example. So use 100 characters and not bytes. Just limit yourself to 1,000,000, not 4 billion or whatever the mathematical limit is. Choosing simple, understandable limits is more likely to make it so people can follow them. And the best thing, of course, the safest procedure is always to reject invalid input. So if anything is wrong, send back an error message and say, send it again. That would be nice. Unfortunately, very often, to keep things moving, programmers choose to sanitize data instead, where they take the bad data and they clean it up and use the cleaned up version. And of course, that invites hackers to just think of a more clever way to encode their attack so the cleanup won't catch it. So explain what constitutes a valid entry, flag multiple errors at once so they can be corrected. When people keep the rules simple and clear and break up complicated forms into parts, I certainly have this kind of frustration a lot on the internet, where they have some form that asks me 10 questions and 2 of them are bad, and I have to keep going back trying to find out what the problem is. All right, if you're getting data from other computers, then, of course, the problem is rejecting is going to stop the whole process, and you don't have a user where you can pop up a box and say, oh, please enter it again, obeying the format rules. So this is why people are tempted to sanitize instead of reject invalid data. However, if you're going, you should at least have clear documentation specifying what your module can handle, so programmers can prepare for it. All right. And so thus you may not want to stop it for a minor error, of course, so you might attempt to correct the input, truncate things, remove spaces, correct addresses, and so on. This is dangerous. Not only might you miss malicious input and let it through, but you might alter the input so it has a different meaning. That is what a lot of people do. All right, and then there's character string vulnerabilities. The obvious one is if something is too long and exceeds the buffer and you're writing in the language like a C derivative, then that'll cause a buffer overflow. Otherwise, it'll just be a performance problem. So limiting the length is good, and you should limit it by number of characters, not by number of bytes. Now, Unicode is the most common encoding, and here one character can be up to 4 bytes long. Some characters are 1 byte, some characters are 2, 3, and 4 bytes. And that's the correct way to count characters and include characters in all modern languages. There are some really bizarre pitfalls in Unicode. One of them is, here for example, is a Latin capital letter I and a Roman numeral 1. These are different characters. This one is 0049, this one is 2160. They are different characters, but they look exactly the same. So these are called homoglyphs or something. These are characters that look the same, but are in fact different characters. So that can confuse people. A homomorph, that's it. So you can spell PayPal with this character instead of a P, and there are some characters that have multiple representations of things that look the same. That's why it's really hard to filter out bad characters. And then there's another thing. Normally what you do is you normalize the input string to a standard form, and then you hopefully know what form it'll be in. For example, if you have integers coming in, then you just evaluate the integer into an integer variable. Now you know it's an integer. But if you have a string of characters, defining its normal form is not that simple. And one thing that could be really dangerous is you convert it to lowercase or uppercase. This is commonly done. But there are characters like this funny looking I here, and this is a test without the dot. That is some kind of foreign character, but when you convert it to uppercase, it converts directly into the real uppercase I. It's not just a character that looks like the I, it really is the I. So by converting it to uppercase, you may miss the fact that the original data used a strange character. So, for example, you can exploit it this way. You're putting in script. You want to scan for scripts, you convert to uppercase. Therefore, to do your test, you convert to uppercase, make sure the uppercase script is not there, and you don't know that this string will pass that test. The uppercase version will be correct. So it's a problem. Anyway, it's the kind of trick you have there. All right, and then of course injection is where you exploit this stuff. Many kinds of injection. SQL injection is the most famous, but you can also put unexpected characters in file paths and have local file inclusion or remote file inclusion, regular expressions, XML, shell commands, like in the ping form where you can add a semicolon and put an extra command at the end of an IP address. Interpreting strings as code if JavaScript uses the eval function, and headers, which we'll talk about later. The famous SQL injection cartoon. This is actually second-order SQL injection through stored data. If the child's name is this name, then when it's stored in the database, it goes in okay, but when it's used later, it executes the second command, drop table students. And so here you see the normal student's name is Robert, so you'd have an insert command that will insert the name Robert. A malicious student name, if you do an insert, you try to do any name operation on this name, then when you insert it, I guess in this case it is going to take effect as soon as you insert it. So now it's going to, the server will see, insert into this table, semicolon, then drop table students. So it will delete the students table. All right. So the vulnerable code comes from this. All of these flaws come from the same thing. You create a line of text and you include data that came from the user without sanitizing it first. So they can sneak in special characters, and that's the problem. Now, you could improve the situation by blocking apostrophes in names. That will not block all SQL injection, but it'll block this most common type. But of course, that will irritate people who really have apostrophes in their names, like O'Brien. So another defense would be least privilege. The software registering students should not be able to delete tables. That would protect you. And so here's the vulnerable code using SQLite. The wrong way to query the database is where you just have a statement with code written by the developer and then code that came from the user just put in the same line with equal power. So that can cause them to be misunderstood. So you can fix the code this way. What you do is you use a library function that understands what it is to add a parameter into a statement, and you just say insert into student's values question mark, and then the student name goes in there. And now the student name is treated as a data object. It is inserted as a data object here. It is not, you can have apostrophes in it or anything you like, and it will not interpret those as characters which cause part of it to be interpreted as code. This is the right way to do it. Use a library that understands I'm inserting a parameter. That parameter is not code. That's the parameterized query defense, which is very strong. Now here's another issue. By the way, up here, remember the attack here involved adding a second command. This one command is supposed to be one insert command, but it was turned into an insert command, semicolon, and then a drop command. Now that might not be possible, and in fact, in the vulnerable code here, they made it use con-execute script instead of, I think, con-execute, which would only allow one command. So that is a possible vulnerability, and you might think that by not using con-execute script, you'd be safe, but there are some attacks that do not involve adding a second SQL command on the same line, and here's one. Change your name to this, A+. And now when you submit a grade, and Robert gets an F, Robert will now get an A+. So there are some commands that do not involve adding a second SQL statement, so even using the single statement executing library call would not be a strong defense. Then there's path traversal for PHP vulnerabilities, local file inclusion. So input is a file name, and you're expected to just load an image from this location. The problem is you can put .. / and traverse out of that folder to some other folder they didn't intend to expose, and now you can read data from somewhere else. One defense is to include only alphanumeric characters or filter out .. and /, but Windows uses \, which is a problem because it has special meaning in Unix, of course. And so here's another vulnerable algorithm. If path begins with .. / reject it. So, but the problem is, if you know a subfolder, you can do a subfolder and then put in more .. slashes, and now your path does not begin with .. It has .. slashes in the middle, but you didn't check for that. All right, and so here's the fixed code, and I've got this live here. Let me clear this. All right, and so if I cat the, here, let me just do an ls, see what I've got. All right, this is safe path demo, I think. Yeah, okay. So if I make bigger, if I cat safe path demo, then this is going to have a function called safe path that will convert a path into a safe path. So what it does is it takes the OS path dirname function, which gives the absolute path of the file to this running script. So this gives me a reference point. And then it takes the file path, which will take the join, the base directory, and the path that came in from the outside. And then it'll compare those two. So the point is, if this is just a subpath, which when appended to the location of the script, gives the real path of the combination, then it's okay. That's the point. Is here you take the base directory and you add the path to it, and here you calculate the common path of that. So if this contains things like .. / or then this will find the shorter path, shortest path expressing it. So perhaps I better make an example of this. Let me bring up a text field. Well, I think the live example will run. Let me run this. Python 3, safe path. All right, so if I put in foo, it correctly says, go to the directory we're in, user sandbound SC chapter 10, and add a foo. All right, but if I try to put in .. / foo, it complains because it notices that the result is not equal to the path of the resulting file path created by joining those together. You've ended up somehow in another directory. By the way, I think a subfolder would be okay. Sub foo. That's okay. And of course, even if I have something, Control C, I hit an extra character. Even if I put in sub, and then I try /// foo, it won't fall for that either. So any attempt to manipulate the path that no longer is a subfolder of the original path, it'll reject it. And that's what you want. That's a... All right, then there's regular expressions, and I've got this one live too. Let me clear this. All right, so here what it's going to do, it's going to look for a string. It's going to look for DD repeated some number of times, and then it must end on a D. So it's going to look for an even-numbered list of Ds that ends on a string. But the way it's going to do it is by trying to match DD, and then it'll try to match DD offset by 1 and have to go back and forward checking. I'm not sure I can explain it in great detail, but the regular expression algorithm is very inefficient. It doesn't realize that this is one D followed by another D multiplied some number of times, ending in dollars here. The way this is written, it's going to have to check the first character, check the second, go to the third, then go back and check the ones before it, and so on. So the result is this can take a really long time. I got to study it again. I've always been pretty weak on regular expressions. I don't quite know why this has to backtrack forward so much. But the point is, if you give it a string like DDDD with an exclamation point on the end, then it doesn't match it. But if you give it a string that does end with an even number of Ds, it matches it. Okay. Now if I give it an odd number of Ds, that also matches. So all it's doing is seeing if you have continuous Ds right up to the end. But it turns out that this is spectacularly inefficient for longer inputs. There's 10. There's 20. And it took 0.01 seconds. So I'm going to copy that. It's going to do something like take twice as long for every additional character. So there's 4 or 5 more. Now it's taking 0.05 seconds. And if I run it again and give it, say, 5 more, now it's going to take 10 times as long, and so on. So it can take a really long time because of the very inefficient process where it keeps hunting back and forth through the string. This is why it gets you in a lot of trouble. Regular expressions can do this, and also packet definitions that are compatible with snort can do this. So you can write a rule to look for some invalid input in, say, network traffic, and you can easily write a rule that is so hard to process that the traffic filter cannot keep up with the traffic. All right, so to avoid letting people create these denial of service conditions, you don't want to let untrusted inputs go into the computations. So limit the length of the string and test the worst case to make sure that nothing the user puts in can result in one of these conditions that is too slow. And XML has a variety of dangers. I've done simple XML injections on some sites where you just inject less than and greater than signs to have unexpected results. But here's the denial of service version. You can do this thing called the XML entity definition. So I can define an entity called big1, which is just big. And then I can define entity big2, which is many repetitions of big1, and big3 that's many repetitions of big2, and so on. So this will do something like multiply, getting 10 times bigger with each layer of iteration until this end result will make 8 megabytes of XML. So you can create a simple denial of service that way. It's like a zip bomb. Zip bombs are files which are carefully crafted, so when you unzip them, they become unthinkably huge and crash the server. When you read a file, here's another thing you can do. You can define an XML entity that reads from a file and then print that out. So you can expose files, sort of like directory traversal. So that's the kind of thing. If you have XML, you shouldn't have untrusted inputs in there. And so input validation is your first line of defense, removing the known dangerous characters, but it often may not be enough. As we said, there may be ways to sneak attacks past your character limitations. Just not using untrusted data in constructed strings is a lot better. You can also use libraries that are safer. Remember with SQL injection, there was a library that would only execute one statement. So that would block people that attempted to attach a second statement. And so here, if you were going to make a command starting with ls and then put in data that came from the user, you might be subject to SQL injection. But if you did a direct system call to read directory, then the only thing it could possibly do is read a directory and nothing else. So in the same spirit as that, it would be less vulnerable. Let's see, check the inputs line length to see whether it is human input or copy and paste or machine generated. Well, I suppose, I'm not aware though, I don't think the length will tell you that, but I have to say this happened to me in my consulting. There was a login form where they say you cannot use a password manager, and they detect, I think, how long it takes you to type it in. And it's true, if you copy and paste it or a password manager fills it in, it won't let you in. They force you to actually type the password. And I think they're doing that by detecting the timing of your tapping the keys. Anyway, also don't just store data in the file system directly. This might be better to use library calls that call functions and such, so you don't have to refer to long paths. Anyway, any way you do it, it's very difficult to anticipate and block all possible attacks. There are source code scanners that can help. Vulnerability scanners like what we're going to use will find quite a few of these, although they're spectacularly bad at it. I remember when I tested it years ago, they don't find all the SQL injections or anything. They often fail, but they do catch some of them, and that's what most people use because it's all you can easily defend your staff to do. So let's try a Kahoot. I've got them up here. Let's see. Can't find the top of the window. There it is. All right. Problem in my dark mode, everything is black on black. All right, here it is, the right one. I see only 5 people in Switch, perhaps 6 now. May not be enough to get 3 competitors in the Kahoot. I'll wait a few seconds and we'll run regardless so people can see the questions. All right. All right, so which defense will prevent shell command injection? Yeah, you make a direct system call. Apostrophes won't perform shell command injection. It's more often things like semicolon that would do that. All right, which operation might change 2 Unicode characters into the same character, 2 different characters? An uppercase. Turning it into the uppercase can be enough to make them in the same character as we saw before. All right. Homomorphs is not an operation, it's just an expression of 2 things that look the same even though they're different. And what's the safest way to handle input that fails validation? If you reject the input, that's the best way, the safest thing. The problem is, of course, you can create a denial of service condition. If you do any of these other things to try to clean it up, then you run the risk that the attack may still sneak through. All right. Well, all right. So that's it for the cahoots. I'm going to stop the recording.